let's look at this thing called implicit differentiation, which apparently sounds difficult. But it's not. It's not that hard. And actually, we've seen it already. It's just another name for the chain rule. That's all it really is. But let's have a look at it. There it is. As I say, exactly the same as we saw with the chain rule. And what it's basically saying is, if you want to differentiate a function with respect to x, but say the pronumeral isn't x, the pronumeral is y, well then what you do is you differentiate with respect to y, and you just multiply it by dy dx. And then if you think of them as like rates, because that's what they are, derivatives of rate, the dy cancels with the dy on the right hand side, and fair enough, you get df dx. So y equals x squared. We don't have to do this implicitly, we actually do this explicitly. So when we have a function, we differentiate explicitly. But to illustrate what implicit differentiation is, and I mentioned this before, what we're actually doing when we're differentiating is we're solving an equation. And what you do to one side, you do to the other. So technically what we're saying is, I want to differentiate both sides with respect to x. And so, all right, I'm going to differentiate the y with respect to x on the left-hand side, and I'm going to differentiate the x squared with respect to x on the right-hand side. But then on the left-hand side, I have a problem, because, well, hang on, I can't differentiate y with respect to x, but I can differentiate it with respect to y, and I'll multiply that by dy dx using our chain rule. And now we'll go and do our differentiation. Differentiate y with respect to y, you get 1. And on the right-hand side, differentiate x squared with respect to x, you get 2x. So what we're really saying is 1 times dy dx is 2x, and there's our answer, the derivative is 2x. Now, of course, we don't put all those lines of working out in, because for something like this, we can differentiate explicitly rather than implicitly. We can just go straight there. But if I had something like this, x equals y squared, so the parabola on its side. See, the problem here is I can't differentiate explicitly because I don't have a function. The parabola on its side is not a function, it's a relation. So I have to do this implicitly. It's all right, looking at it the same way, I want to differentiate both sides with respect to x. So on the left-hand side, that's not a problem. But the right-hand side, it is a problem. Because I can't differentiate y squared with respect to x. But, just like I was doing before, if I want to differentiate y squared with respect to x, what I'm going to say is, well, I'll differentiate y squared with respect to y, and then I'll multiply it by dy dx via our chain rule. So when I'm doing my working out for this one, I don't actually put this middle line in. Normally, I would just go straight to the third line there. So on the left-hand side, what I say when I'm doing this calculation is, okay, can I differentiate with respect to x? Differentiate x with respect to x, oh, I get 1. Then when I do the right-hand side, I go, oh, y squared. Well, I can't differentiate it with respect to x, but I can with respect to y. So I'll do that, 2y, and then multiply by dy dx. And then I get a formula for dy dx. But instead of my derivative being in terms of x, it now is in terms of y. Now that makes sense if you think about the shape. We've got a parabola on its side. If I want to find the slope of a tangent, if I was to sub an x value in, there's 2 possible points for the x value. So you get 2 different answers. But if I substitute the y value in, then there's only 1 possible point. So I get the exact point that I want. So that's the advantage of differentiating implicitly. If I'd wanted to do it explicitly, I could. I'd have to rearrange the equation and make y the subject. But then I'd have to make a choice about whether I'm going to take the positive square root, the top half, or the negative square root, the bottom half. So I'd have to make a choice. So if I wanted to differentiate this sort of function, so the term is x squared y cubed, I'm going to have to use a product rule. So I've got 2 things multiplied together. So I would say, write down the first x squared, diff the second, y cubed. Well, hang on, I can't differentiate y cubed with respect to x, but I can do it with respect to y. So it becomes 3y squared, and I'll multiply that by dy dx. Plus, write down the second, y cubed, that's fine. Diff the first, differentiate x squared, we get 2x. So our derivative tidies up to be, a lovely expression there, 3x squared y squared dy dx plus 2xy cubed. But here's where it's really good. If I want to find the equation of a tangent to a circle, so again, a circle is not a function. Okay, x squared plus y squared is equal to 9. Not a function, so I can't do it explicitly, so I'll do it implicitly. Differentiate x squared, that's fine, 2x. Differentiate y squared, can't do that with respect to x, I'll do it with respect to y. So I get 2y, but then I've got to multiply by dy dx using the chain rule. Then on the right hand side, differentiate the 9, I get 0. I can rearrange that to get that eventually, there it is. The derivative in this one is minus x on y. So I need both an x value and a y value for this one. Now if you think about a circle, that makes sense. Because if you were to just use an x value, you're going to have 2 possible y values. If you were just going to use a y value, you'd have 2 possible x values. So to isolate this one, I need both the x and the y value of the point to find the exact slope that I want. So we're at the point 1, 2 root 2. Sub that in, we get the slope of minus 1 on 2 root 2. And point slope formula. So it's all pretty standard from there. So we get x plus 2 root 2y minus 9 is equals 0. So that's the real advantage, I guess, of implicit differentiation. I don't have to rearrange that to make y the subject. I can just go bang, there's my derivative. Okay.